So now we have to talk about. So before starting the class, I would request you to please turn on your webcam so we can continue. Right.
Okay. Okay.
Okay. Have you opened your camera? Like I'm not able to see.
Yeah, it's not loading. Oh, just 1 minute, 1 minute, 1 minute.
Okay.
Okay, now it's working. Okay.
Okay. Great. So let us start. So we have to talk about what? Internal energy, right? We already discussed it, how internal energy works. It is a heat change basically, but we fix something. What was the thing that we fixed? If I say it is a heat exchange, it is a change in heat, but what specific thing I need to like make constant to in order to say like it is internal energy. You remember what is internal energy and what is enthalpy? We talked about it. Basically, both of them are change in heat, but
Yeah.
how are they different from the normal heat exchange?
Okay. Internal. Okay. Internal energy is when the volume is a constant. Is that correct?
When volume is constant, the heat exchange that you are observing at that point, we will call that change in internal energy, right? So as
Mm-hmm.
from the first law of thermodynamics, what it states? It states that your change in internal energy is nothing but your work done plus your heat, right? So now if your volume is constant, and we know that work done can be written as P delta V, right?
Yeah.
If your volume is constant, that the change in volume is going to be zero. If the change in volume is going to be zero, then your Q at constant volume, this V indicates that the volume is constant is nothing but your internal energy change. So whenever you are observing a heat change at constant volume, that you will say that it is nothing but change in internal energy that we have proved here. Is it making sense?
Yeah. Yeah.
What about enthalpy? Enthalpy is when you are observing a change in heat, but now what condition is constant? Your pressure, right?
Yeah.
At constant pressure, whenever you are observing change in heat, you will call it enthalpy. So let us see how we can use it with the help of our what? Our first law of thermodynamics.
Our
What is the
yeah. Mm, the
this is
formula.
the first law of thermodynamics. What I did here, I put this thing.
U is internal energy,
Hmm,
Q is heat,
hmm.
and W is work done.
What I did, I just transferred my W on the left hand side. So what I observe that I am going to have a negative sign here. But
Yeah.
when I am talking about enthalpy, I will consider that the work is done on the system. For work done on the system, what sign we use for work done? If I am working on the system, the W is going to be positive or negative
Um, if work is done on the system,
on
right?
the system. Yeah,
Then the sign will be positive.
positive. So by normal mathematics, what we observe, we observe the negative sign, but we have to consider the work is done on the system. So I
Positive.
convert it into positive, right? Is it clear why I use
But
positive?
how would I know that the work is done on the system?
For enthalpy, we usually consider the work is done on the system. In this formula, you have to consider the positive sign only,
Okay.
everywhere, right? So if I am talking about Q and the pressure is constant, what will I call it? Enthalpy, right? H is
Yeah,
represented for enthalpy. So
H
what
is
formula?
enthalpy.
So what formula we have with the help of our first law of thermodynamics in terms of enthalpy is this. Your enthalpy is nothing but change in internal energy plus PV. PV is your normal work done, right? Now the
Yes.
question is, we cannot calculate the exact value of H. We cannot calculate the exact value for enthalpy. For that, we need to use statistical thermodynamics. That is not in your syllabus right now. So what we can calculate
Okay.
now? We can calculate the change in enthalpy. How much change you
Change
are
in
observing
enthalpy.
in enthalpy, we can calculate that. So for change in enthalpy, what we are going to do is, see, enthalpy, this is the definition. See, what is enthalpy change? Enthalpy change is your enthalpy of a system in final state, you will subtract it from its initial state. This is nothing but your change in enthalpy, right?
Yeah.
So what you will do, if this is your equation 1 and this is your equation 2, you will just put the 2 in 1, equation 2 in 1. So what you will observe?
How?
This is your delta H, right? If you are talking
Yeah.
about H2, if you
Oh,
are
like
talking
that.
about
Okay,
H2,
okay, okay.
H2, then here you will have to 2. So you will put this here,
Oh,
and after subtracting, you will get this final formula which you are going to use in question solving, right? So after solving, if P is constant while the gas is expanding, then you will have this volume. This is the formula of first derived from first law of thermodynamics for change in enthalpy. The change in enthalpy is nothing but change in internal energy plus P delta V.
wait,
Right.
I didn't understand how. What did he do?
See, let me do it here. This was your formula for the
For
enthalpy that we
enthalpy.
calculated. So what we did, we use this into this. So how? Let us see. If I am writing H2 minus H1 is equal to,
Hmm.
now what is del U basically? Uh, if I am telling U2 minus U1 is basically delta U or not? Delta U
Yes.
is nothing but this thing.
Delta U is this one only.
Now, now, if I am doing the same thing with respect to this, if I am see, let me write it back. H1 is going to be delta U plus P1 V1. H2 is going to be delta U plus P2 V2. What I am doing basically H2 minus H1, which is going to be U2 minus U1 plus P1, sorry, P2 V2 plus P1 V1. What I'm going to do is I will take the two, like P2 V2 with the U2 one, right? The U2, which is internal energy 2, I will take all those values which are having 2 in there collectively. So what I will do, I will write it like U2 minus U1, then this is going to be minus P2 V2 minus P1 V1, right? This is nothing but change in internal energy, and this is what?
How do
This
you
is,
wait? How did you get to P2 V2 minus P1 V1?
see, look at it. What I am doing, just see it. This is your P1 V1.
P1
This is
V1.
your P2 V2, right? What I'm doing, H2 minus
Yeah.
H1. This entire thing is going to be subtracted by this one.
Volume is the same thing, right?
Volume is going to be V2,
Okay.
right? So
Then yeah,
after
I understood.
subtracting it, we will get something like this. And this is nothing but change in PV. P2 V2 minus P1 V1 is delta PV.
Okay, I understood that part. But what about the delta U?
The delta U is
Won't
going
it
to
be
be the same.
like
U2 minus U1.
how
See, what is delta? Delta is change. Change is with respect to
change?
something. Final minus initial. Here, what we are doing?
Yeah.
Final, final pressure, final volume minus initial pressure, initial volume. This is also change.
Okay.
Is it clear?
Yeah, just 1 minute, 1 minute.
So
Oh, okay, okay, okay. Oh, yeah, I understood, I understood.
yeah. Now, as for enthalpy, pressure is constant, right?
Yeah.
Pressure is constant, so we will take pressure out. Like the pressure is constant, so we only talk in terms of volume. So the final formula that you are going to use is this one. Your enthalpy is nothing. The change in enthalpy is equal to change in internal energy plus P delta V. This is your formula.
If
Mhm.
pressure is constant, then the delta P should be zero, right?
Delta P will be zero, but we are not using that. We are just talking in terms of, see, suppose P has a constant value. If P is constant, then it is going to have a constant value. Suppose let it be 5. And you said it correctly.
Huh.
If we are taking the change in pressure, it is going to be zero because 5 minus 5 is going to be zero. So that
Yeah.
is the reason we are going to take it as a constant outside of our delta,
Okay.
right?
Fine. So we can do that
Hmm.
somehow.
Not somehow, it is constant. See, whenever you are doing differentiation or integration, you will take the constant outside.
So, okay, then what if it's not a constant?
If it is not a constant, that we have to consider that as well.
We need to
The
consider
change.
that same
Ah,
thing.
the,
The
we
change,
will
which one? The first equation or second equation?
if your pressure is not constant either, then we have to use this one. The pressure is going to be, suppose if pressure is not constant, it is changing. P2 would be
Hmm.
something else. Let it be 5. P1 will be 2. So the change is going to be significant. 5 minus 2 is 3.
So we need to use the first equation. So
For
if it's
for this, if pressure
four,
is not
if
constant.
not, yeah, but it is, if it is constant, then we need to use the second one. But enthalpy
For
is always pressure is constant
always
though.
pressure constant. Yeah, that's
So
right.
we always use the second equation though.
Yeah. Yes.
Okay.
And one more question in your exam, they might ask you, what is enthalpy? Is it a path function or state function? See, your change
Mm.
in heat is path function, but your enthalpy or internal energy is a state function because it depends on the path. If you are going with constant pressure, it is going to be enthalpy. If you are going through constant volume, it is going to be internal energy. So it is dependent on the state of the function, right?
Okay, fine.
But your simple heat is going to be a path function.
So enthalpy is a state
State.
function.
Q is path function, but your enthalpy or internal energy is state function.
Okay.
Right. Now let us see some questions.
Heat is a path function, right? Heat.
Normal heat is path function.
Okay.
Okay. So now here what we have a question. See, the question is saying heat absorbed by a gas at constant volume is 300 joule. What you have given? Q. And we are talking about constant volume, then we will use QV. And QV is nothing but internal energy. You have given internal energy.
Yeah.
Then you have to tell the statement which is correct. So the answer is also given. So can you tell me like why the fourth option is correct?
Fourth option. Okay. Heat absorbs by gas at constant volume
Mm-hmm.
is 300 joules.
Yeah.
Then, which statement is correct? Okay. If the volume is constant, then its internal energy. Um, so delta U is equal to pressure plus work.
You
Correct?
are
No, no, no.
simply
Sorry.
saying,
Delta U is equal to Q plus W, right?
okay.
Yeah.
And this E is
S-
basically U. This E and U has same
okay.
meaning. E and U is internal energy.
Okay. Um. Okay. Internal energy is equal to heat, which is equal
Now,
to
now try
300.
to expand this formula. Try to expand the W.
W is equal to 0.
Minus P
Um,
delta V. Your W is P delta V,
okay.
right? And
Yeah.
delta V is what?
Okay. This is easy. Uh, Delta V is 0 because volume is constant. So
Hmm.
if volume is constant, then the change in volume should be zeros because 0.
So the W will be
I
0.
mean, yeah, so W will be 0.
Now, what else it is given in the question? It is saying absorb. Heat is absorbed.
Yeah.
If heat is
Absorbed.
absorbed, that means positive value.
Yeah.
Endothermic.
It's towards the system, right?
Yeah. So the
So
fourth
it's
option is
positive.
hmm,
So yes, internal energy is equal to Q because
hmm.
the W is 0. This is equal to 300 joules. That's correct.
Is it making sense?
Yeah.
Okay. Let us see
But
the next one.
why is there like 300 joules equal to W, which is equal to 0?
Uh, See, this is
Is
basically
it
this
is it a
confusing.
typo? What is this?
No, 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 both are the same thing. You already you yourself solved me.
No,
You
not
said,
delta E. I'm saying like there's a equal to sign. Shouldn't there be like
see the
comma?
thing that I'm writing. As the W is 0, right?
Mm-hmm.
So your internal energy is nothing but Q. Both are same.
Mm-hmm.
So you
Yeah.
can write it either way. Delta U is equal to Q is equal to 300 Q.
Yeah, that's fine. But which is equal to W?
Okay, here this is.
Yeah, that's what I'm saying. Okay.
Let's see the next one. In a closed insulated container, a liquid is stirred with a paddle to increase its energy by 500 joules. Then which is correct? So try to think about it.
Liquid is stirred with a paddle. What's a paddle?
Normal, this paddle thing like piston. You can imagine it like a piston.
Piston.
Uh, Piston would work.
Okay. Stirred with a piston? Or that?
Have you seen like to uh, 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 ha, ha, ha. In the in boats? Have you seen those paddles that are pushing the water?
Yeah.
That kind of thing. This is that kind of paddle.
Okay. So like a spoon then.
You can say.
Paddle to increase its energy by 500 joules, then which is correct?
Mhm.
A closed insulated
Container.
container. Insulated. What's insulated?
For insulated, like the temperature is constant.
Okay,
And
temperature is constant.
if you are saying closed container, then one more thing is going to be constant again.
Um, temperature.
Insulated temperature and
Wait, closed container, right?
uh,
So, matter is constant, but matter is constant.
matter is not exchanging from the system and surrounding. We are trying to say that
No, I'm
because
saying is that temperature is not constant.
it is. See, try to think about. We talked about the open cup of tea, then a
Yeah,
cup with covered, and then the one where the energy is not insulated, like the adiabatic. You are remembering
yeah.
where the heat as well as matter is not exchanging. So where we observe the
So
Q is
that's
constant.
what this is.
Q is constant here.
Okay, then Q is constant.
Hmm. Again, you
Um,
have to apply your first law of thermodynamics.
if Q is constant, okay, Q is constant. Is volume also constant since matter is constant?
No, we should not take the volume as constant because we are talking in terms of liquid. It is very hard to make it constant because like if it was a solid, then we could say that volume is constant. But if we are talking about liquid or gas, the volume is not constant because the change is significant.
Yeah.
That's why I have like
Okay.
we have
Let's take the first option. Okay, internal energy is equal to 0. Can it be zero?
Yeah.
Q is constant, right?
Yeah. This is your formula Q plus
Q,
W.
yeah,
Delta U is equal to 0 plus W. Delta U is going to be W. As the volume is not constant, you are going to observe some work done. If there is some work done, there is going to
yeah,
be some internal energy as well.
yeah. So first one is not correct because everything is zero, so it doesn't matter. That doesn't make sense.
Hmm.
So second one, yeah, second one, internal energy is equal to W. That's correct, and W is not equal to zero. That's correct, and Q is equal to zero. So that's correct. No, everything's
This
correct.
one,
Second one,
right?
yeah.
So,
Third one doesn't make sense. Fourth one, no, it doesn't make sense.
okay.
If
Now,
W is zero, then the whole thing is zero. How will
right.
that make sense?
So let us see some more questions. Hmm. In an isothermal,
Mm.
in an isothermal, volume of a gas is increased from 1 liter to 2 liter. If heat absorbed by the gas is 500 joule, then find change in internal energy in calorie. Take R is your 2 calorie per mole. This is your I have written like how the R real gas constant is going to vary from different for different SI units. Right? For calorie it is 2, for joule it is going to be something else, and for like
Mhm.
liter it is going to be something else. So what data you have? You have V1
V1, yeah.
initial volume,
I have
final volume.
V1 and V2.
Mm-hmm.
Um, Q isothermal. In isothermal, isn't temperature
Yeah, it is constant.
constant?
Good, good, good. Yes.
So Q should be zero, right?
I told you in the previous class, temperature and heat are different things.
Oh, okay, okay, okay. Yeah, 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 yeah. Yeah, yeah.
Now, what
Mm,
else do we have?
heat is
It is saying
absorbed
heat
by
absorbed.
500 joules. So
That
it's
means positive.
positive.
Good.
Um, then, okay. So, internal energy is equal to Q plus P delta V. Can we use that?
Mm-hmm.
P delta V. So Q is 500. So delta U is equal to 500 plus we
Into
need P though.
just think about in the application part of thermodynamics. Now, I told you something. Whenever the temperature is not changing, then your
Uh-huh.
internal energy is going to be constant. What is internal energy basically? Internal energy is due to your gas molecules,
And
right? If your gas
okay,
molecules are having a same temperature, right? Suppose
okay.
they are all having same temperature, then there is not going to be a change in internal energy. So if the temperature is constant,
Uh,
the internal energy is going to be zero. It is constant. Suppose you are subtracting basically what is delta E. This is you can write it like U or E, both are same thing. So if your internal energy is constant because the temperature is constant, then a constant minus constant for change is going to be zero.
zero.
So whenever you see isothermal processes, the internal energy is going to be zero.
But isn't like
Mhm.
um so if internal energy is constant, that means
The temperature is constant.
the temperature is constant. So wait, just 1 minute, 1 minute, 1 minute. Internal energy is when the volume is constant, correct?
Internal energy. No, we see. This is your simple formula, right? Q plus
Yeah.
W. And how can we modify it? Q minus P delta V. If your volume is
Mm.
constant, then you will say that your heat exchange is your internal energy.
Is
Suppose
Q.
is Q. This one is constant, so this is zero. Then del U is going to be Q V, which is your internal energy itself. But if your temperature is constant, suppose
Okay, okay,
inside
okay.
your mixture, inside your system, you have number of gas molecules, right? If
Uh-huh.
your temperature is constant, those gas molecules are
Mhm.
not going to experience some thermal energy. If the thermal energy they are not experienced, that they won't move, right? Suppose, let me use some other. You are sitting in a room, right? And the temperature is 25 degrees Celsius. Your room temperature, your like the condition are good, very good. You won't be doing anything. You would be just laying on your bed, right?
Yeah.
Suppose you are a gas molecule, but the moment I increase the temperature, you will start to walk around, right? If garmi lag rahi hai, you will try to go out from
Yeah.
the room, right? So the
Yeah. Yeah.
moment
Yeah.
you are changing the temperature, your internal energy, you are a gas molecule, your internal energy is going to change. But if the temperature is constant, then your
Mm-hmm.
internal energy is also going to be constant. You are just going to sit around a place.
Okay.
Have you revised like? And one more thing, I have uh, trimmed these notes. I have removed the advanced A advanced part so that you can only focus on your CBSE part, right? Now the PDF is very easy. Just give it a read. I will share this PDF after the class. You will find it very easy now. Right?
Okay. Okay. Just 1 minute. I want time to think.
Think about it and please try to revise. I will share these
Uh-huh.
notes and they are more systematic, so you will find it easier to read.
So then find the change in internal energy in
Calorie.
calories.
Yes.
So they want
This
me to
uh,
find internal energy.
see the extra data is just to confuse you. Your answer was done by this small data. You saw isothermal, there is no internal energy, like no exchange in no change in internal energy. So after seeing isothermal, you shouldn't like the extra data is just to confuse you.
Okay, but so
Mhm.
if internal energy is zero, right?
Ah,
And they are telling me find the change in internal energy.
yes,
So should we say zero?
yeah, just zero. You should say delta U is equal to zero. That's it.
That's it.
Yes. Suppose you haven't studied this concept very well. What you will do? You will waste your time, right? You will try to
So the
find.
whole question was for you to confuse, and the only
Ah,
three words you need to know is
isothermal.
it is in an isothermal, and that's your answer.
Yes. But just imagine you haven't
Okay.
studied this concept very well. What you will do? You will just try to waste your time, right? You will try to find the
Yeah.
internal energy. So this is all uh, the data is given to confuse you basically, so that you can waste your time in exam, right?
Okay.
I
Yeah.
hope, see, if you try to go through the previous concept that we have studied so far, na, and after that, if you
Mhm.
see these questions, you will find them very easy. The good thing about thermodynamics is in your exam, they are going to ask you very easy questions.
Not for my school, but okay.
Okay. So the
Questions haven't come yet, so I don't know what they will ask and what lesson are coming for half yearly.
I think your summer break is going to be till last of
And
August. Your classes will resume from September, I guess, right?
yeah, I think.
So you don't have to worry about it. Just revise the things that we are discussing today. If you have time before sleeping, just go through it. That way, you will have like the concepts will be fresh, and if you just read it again, that it will help you to like retain them for a longer period of time.
Yeah.
So what I can do now is I am giving you these questions as homework. The answer is already given. I will ask you in the next class why this answer is like this, right?
Yeah.
You have to explain me why, right? Mhm. Now just give me 1 minute. Okay, where are you? See, now we have to do the sign convention the way we did for the previous concepts. Here we have to do the same. Now, what is enthalpy? Enthalpy is represented by H, and what does it represent or signifies? It signifies the change in what heat at constant pressure. So, if basically your heat change in enthalpy formula is this H2 minus H1. So if your H2, that means final enthalpy is greater than your initial enthalpy, the process is endothermic, and you are going to get a positive value if you are measuring the change. So now you know why we use positive sign for change in enthalpy for endothermic processes, because the final
Yeah, you
enthalpy is
explained
greater,
this.
right? And this is for negative, and the same concept goes like this. The SI unit is calorie
Yeah.
per Kelvin or kilo Kelvin joule.
Will
Kelvin,
they give
calorie.
us how to convert them?
Uh, they might give you, but you will find the data like
Like
what
the
is.
above one, the above question we have done.
For that now, I would like you to see this. Mm, this small table, you can see if your SI unit is joule, you will use this value. For calorie, this.
Uh-huh.
For liter atmosphere, this. And if they are asking you to convert, you can do that as well.
Wait, just one
So,
moment. Go back, go back. I want to check whether I have taken that screenshot or not. If I had, we can continue. Otherwise, I'll take a screenshot. I think I haven't. I'll take a screenshot, okay?
okay, please do. Then let me know.
Okay, you may continue.
Right, two seconds. Yeah. All right. So let us move ahead. What we need to do is. So now a relationship between your internal energy change and your enthalpy change. So what we know that your enthalpy is H is equal to U plus PV. And if we are taking the change, that we can say change in enthalpy is equal to change in internal energy plus change in PV, right? Is this
Mm-hmm.
formula making sense? We just discussed this. How it started? Uh, we are taking things at constant pressure.
Constant pressure.
Yes,
Isn't it like delta H is equal to delta U plus P delta V since P is constant?
are you seeing this one? This formula,
Yeah.
the normal formula, right? So what I'm doing is I am taking constant pressure. So the Q will become QP. And what do we
Uh-huh.
know? QP is nothing but H plus
Heat.
W. Can I
Yeah.
write
I
it like
mean,
this?
yeah. Enthalpy. Yeah.
And I can write it like this. I will put this over here. And what I told you,
Yeah.
whenever we are talking about enthalpy, we will take
It's
work done on the
positive.
system. Right, good, very good. So we have this formula like this one.
Yeah.
So now here we have change in internal energy. So what if we are talking about change in enthalpy as well? So if I'm talking about change in enthalpy, I will put this delta sign over here, and I have to do the
Okay.
delta sign over here as well.
Oh,
Okay, is it making sense? Be
yeah.
honest. Okay.
That kind of makes sense. The only thing that is bothering me is that it is constant pressure and
Yes.
delta P.
Delta P or delta P?
Constant
Huh?
constant pressure
Uh,
and there is a delta P V. Won't it be like zero?
see, you are good, good, good. You are saying delta P V. So
Mhm.
you are thinking like delta P should be zero because constant pressure, right? Pressure is constant.
Yeah.
So try to see. This delta is over to this entire thing. This is a bracket, right?
Hmm.
If I am opening this bracket, what will happen? This P, as it is constant, it will go outside the delta, and we will observe only this P delta V.
Okay, okay.
Okay, now the pressure is constant and it is outside the delta, so it is not going to be zero. And the thing you said is correct. If if we
If
would have taken like delta P, and as it is constant, it is going to be zero, and the entire thing would have
mhm.
been cancelled out. But here it is not like that.
Yeah.
Now, for ideal gas, right?
Okay.
If we are talking about expansion or compression processes like expansion or compression, then this formula is going to go like how? We know PV is equal to nRT.
Yeah, PV
So
is
can
equal
we
to
replace
NRT.
PV is equal to this? Can we replace PV?
Yeah, delta NRT.
Good. Now N is constant, R is
R
constant.
is also
What
constant.
what is the only thing that is
T
going to change? Temperature.
temperature. Temperature is
So
not constant.
for expansion or compression processes, the delta enthalpy formula can be converted into this as well, right? For expansion or compression. But what if we are talking in terms of chemical change? For chemical change, let us see what is happening. And this is important concept. I will show you some questions on this specific concept. So please focus on this, right? So let me show you. The thing till here is same. We have a formula, we
Mhm.
replace it with PV is equal to nRT, right? Now. It is a chemical reaction, not a expansion or compression process. It is in a chemical reaction, what you observe usually. The number of basically reactant converts into product and there are change in number of moles or not. Number of moles
Yeah.
changes for a chemical reaction. So here, what we are basically doing is the temperature is going to be constant for chemical reaction here and it is going to be zero.
So,
The thing which is going to change for chemical reaction is your number of moles.
oh, we're just playing with those one, three
Uh,
things.
yes. Okay, so if the temperature is constant, this thing is going to be zero. And the only thing that we are going to get is this one.
What
Now,
is
the thing
NG? Won't it
Ng
be
means
delta N?
a delta N. G signifies the number of moles of gas molecules only. I will show you why. N is number of moles, and this G is signifying that we are only considering the moles of gas.
Yes. Oh, okay, okay.
Okay, let me show you what I'm trying to say. Just give me.
No, I understood.
Quick. Let us take an example. So
Okay.
for this reaction, we have something A which is solid, B which is gas, and it is reacting and giving us what? C plus D, and both of them are in matlab gas phase, right? So if I have to calculate the delta Ng, so it is going to be number of product of gas minus number of reactant of gas. So NPG minus NRG, right? So let me write it as well. While calculating
Mhm.
number of moles, we only count moles of gas. If you are supposed to find the change in number of moles, you will only consider gas molecule. So by this
Okay.
thing, if for first case, if del Ng is zero, that means delta H is going to be delta U. Suppose this thing, this thing is zero, then this entire thing will become zero, right? So your
Yeah.
delta H is going to be nothing but delta U,
Okay.
right?
Yeah, that's okay. I have one
Okay.
doubt,
Please ask.
but it is previous.
No worries.
In expansion or compression, right? And
Yes.
the formula we got enthalpy is equal to internal energy plus
Mhm.
nr delta T,
Temperature.
right?
Yes.
Okay, but they said expansion or compression. So for
Mhm.
this is applicable for compression only, right? Expansion
Expansion.
won't it be like a minus?
Uh,
Since
no.
compression is like energy to work done towards the system,
Oh,
and expansion is
good.
a system doing the towards something.
The
Won't it
sign
be
will change.
minus
Good. Sign will change. You are correct. If you are taking, this specific example is for
if you're
compression.
taking expansion?
Expansion, you have to change the sign as per the sign convention. Very good. Your point is valid. Good. I will see. This is a generic formula. While we will be using it in the actual questions, now you will see like we will be using somewhere negative and positive depending on the given
Yeah,
data in the
but
question.
I might get confused whether I have to
Good.
use minus or plus.
We can do this plus minus.
Oh, you have done plus minus. I didn't realize that.
I just did it. I
Oh,
haven't.
okay, okay.
Right?
Yeah, yeah,
Is it better?
yeah.
Now, what if delta Ng, which is change in number of moles of gas, is zero? That would that would basically means your enthalpy is greater than your internal energy. Why? Can you answer this? If this value is greater than zero, then why your enthalpy is greater than your internal energy? And if
Mm,
then it is going to be less.
because
See, if this is your delta H, right?
yeah.
And let us say
Yes.
that both of the delta H is equal to delta U plus RT and G. So if I'm taking my delta H is equal to 5 and this is also
Uh-huh.
5 and this value
Uh-huh.
which is delta Ng
Uh-huh.
is greater than 0. So if it is greater than 0, it is going to add something. Suppose it is after solving this, I am getting 1. So your delta H is what? 5 plus 1, 6. So the delta H is greater than your delta U. Delta U was 5. So whatever, like if your delta Ng is greater than 0, it is going to increase the overall value for your delta H. Are you getting what I'm trying to say? Because here we
Yeah.
have a sign for addition.
Mm-hmm.
Okay, let me take another
So
example.
wait, just 1 minute, 1 minute. How? Okay. How do you get five as internal?
This is a random number.
I know, but like, what if that is zero?
If this is 0, then see you will have some value which is going to be this. So then, if it is zero, then
Mm-hmm.
the number is going to be like it will entirely depend on the on this value. If this value is greater than your delta H, then we will say something else. So it will depend entirely on this one. If this is 0.
Okay. Then if RT delta NG is
Mhm.
zero, then won't how wait, how will it say wait, just 1 minute, 1 minute, 1 minute. So
Suppose
if
suppose
N delta NG is zero, then you're saying that enthalpy is also zero?
no no. If delta Ng is 0, right? This thing is going to be
Mm-hmm.
0. Then your delta is
Oh,
going to
okay,
become
okay,
delta U.
okay. Okay, yeah, I understand, I understand. Yeah, I understood.
Right? So, and
Yeah.
when it is going to be 0, when your number of product and number of reactant are going to be 0. When these two things have same number, then the change is going to be 0. Right? And
Yeah.
if your product has higher number of gas molecules, suppose the product is 5 and reactant is 3, then you are observing this thing. And if your reactants are high, then you will get the negative value which is less than 0.
Is
Right?
there a question for this?
I will show you. Let us see the questions directly. Just for like 1 or 2 minutes, see the entire thing, both of these, and
Can
then
you
we'll
show
go
me
to
the
the answer.
heading for a minute? Oh, this is only applicable for gases. Okay. Delta and D is the same thing, right?
Which one?
Delta and D.
Where is delta MD?
No, I'm just saying delta and D is the same thing, right?
Yeah,
Both.
see the delta is a change where the numbers are not that small. That this CC, this triangle,
Okay.
This triangle is for a change which is having a significant value. This delta is for a smaller change. This is for a like significant
Oh,
change, but this is even smaller change. And if you are using this one,
okay,
then even smaller change. Sorry, not this one, this one.
okay, yeah, okay. ND delta NG. I just need to know that
Mhm.
in chemical reaction, moles are not constant,
Yes, because
and
of the
in
molecules are
expansion and
increasing.
compression, temperature is not constant.
See, if you are talking about compression or expansion, try to imagine it like this. You have a system, and in a system, the number of molecules are going to be constant. The only thing
Mm-hmm.
that you are doing is you are compressing the entire system or expanding it. Is it going to change the number of molecules? No, because the number of molecules are
No.
fixed. But in a chemical reaction, you are making a thing which is entirely new. What are chemical reactions? Let us say, I told you in the initial chapters, if you have H2 and you are reacting it with what? O2 and you are getting
Mm,
H2O, right? So this is a
yeah,
chemical
that's
reaction.
understood.
This is a chemical reaction. Here, the number of moles are going to change. On the left hand side, you have 1 mole of this, half mole of this, and you are getting 1 mole of this. So to make it simplify, let us see like this. So on the
Yeah,
reactant side,
understood.
you have 3 moles. On the product side, you have 2. So the number of moles change, molecules changes for a chemical
Yeah.
reaction.
Okay, fine. I understood. We can continue.
Okay. So let us see this question. Assume each reaction, each reaction is carried out in an open container for which reaction let me see what we have. Assume each reaction is carried out in an open container for which reaction you have given delta is equal to this. So I think there is some happens. See, I will check this question. I think there is some misprint or the PDF is gone. Okay, leave this
What?
question. I think some data is missing from this question. I will recheck it.
Okay,
Let us do this one.
fine.
Or before that, this one. For the reaction, you have C3H8, which is reacting with oxygen, and it is giving this at constant temperature, right?
Uh-huh.
Temperature is constant. So they are asking you what is going to be del H minus del E. So for this, what you need to remember? You need to remember for a chemical reaction where the temperature is constant. What formula do we
Temperatures
use?
is constant. So we
Delta
need to
H is
use delta H is equal to delta U plus NT delta NG.
this one, I guess.
Yeah.
Right. Now, what data do we have? We have to calculate this delta Ng. For delta Ng, what we need?
We
We
need
need product
we need
number of.
wait, we
We need,
need number of moles, number of moles.
so try to see it carefully. For delta Ng, we need number of moles of product in gas form
Hmm.
minus number of moles of reactant in gas form. So this is your product, this is your gas. So,
Huh?
sorry, this is your reactant, this is your product. The right side one is product, the left side one is your reactant, right?
Yeah.
Now, the thing that we have to take should be in gas. So this is in liter, which is liquid basically. This is in liquid, so we won't consider it for the delta Ng. So what we are going to do? We have 3 moles of CO2 in product side, right? On the reactant side, how many moles do we have?
CO2, okay, okay, okay. Gas one, right?
Only gas. Product
Three,
minus reactant.
only gas. Three, three plus. Uh, 2,
Where is 2?
O2, right?
No, no. See this entire thing. CO2. How many moles of CO2 do we have? See.
3. Oh, like that. Okay, okay. Then
Yes.
5.
Uh, how 5? Only 3. This
Mm.
stoichiometry is signifying the
So
number
what
of
about
moles.
the not the product, reactant?
We will minus it. In the productant side, we only have 3 moles of
Mm-hmm.
gas and minus this 5 plus 1. 5 plus 5
Oh,
plus 1,
okay, okay, okay.
6. So the delta Ng is going to be
Minus 3.
now. What you will do. Uh, what what is the question asking? See, this E is U. E and U are same, right? So they are asking you
Oh,
what is going to be the value for
what is
delta H.
delta H minus delta U?
It is going to be this delta Ng you got minus 3 and the RT is going to be as constant. So this is going to be minus RT, minus 3 RT.
That's it.
Yes, that's it.
What about delta U?
They are asking you this now, so you have to answer in that way. If they might
Wait,
have
just
asked
one
you
minute.
about delta U, then
Mm-hmm.
they should have given you the delta H as well. So what you will do? Delta U, then you will like place the delta H on the right hand side, and then you
Oh,
will
okay,
write
okay,
down.
okay, okay. Oh, okay, 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 okay. Yeah, yeah, yeah.
Is
Yeah,
it
I
clear?
understood. Yeah.
The questions are going to be pretty simple. You don't have to worry about it. Say this one. This one is given.
If they ask find delta U, what do I have to do?
See, if they are asking you to find delta U, then they will give you the value for delta H as well. So then what you will do? Uh, this is delta H minus delta U is equal to minus 3RT. If they are asking you about delta U, then you will write it like you will do this and yeah, delta H minus 3RT. They will give you the value for delta H. They will give you the value for temperature. The temperature is given. The temperature is given and R is constant. So after putting the values, you can calculate the delta U as well. And you can do the same for delta H as well, but they have to give you some data, right?
Okay. And do we end the thing equation in minus 3RT?
Uh,
Temperature is given, right?
See the temperature is 27, right? You can put the
Mhm.
27 temperature, right? And the R value is constant that you can use here. You can use the
But
0.81
they
or
haven't given R.
you have to learn the R value. See, you have to
Oh
learn these
my.
three. You have to learn the calorie one is
There
very simple.
were, okay, but we already went through a lot of constants in the first two lessons. There's more constants coming.
You will face few more constants. The major chunk about the constants were for the second chapter, I guess. In second chapter, you have came across so many
Yeah,
constants, Planck and some other
Redbergs.
constants, Rydberg. Here you have to deal with the constants, but uh, they are not going to be that much. If you learn this R value, it will help you to do the most of the questions. See, if your units are like joule, mole, or Kelvin, basically
Mhm.
joule, then you will use this value. If it is in calorie, you will use this value. If it is in liter atmosphere, you will use this value. You have to learn these three values
And
only.
what do we use in our equation? Is it in cal?
The one that we are solving right now,
Mm.
in that question, they haven't given the data, right? They haven't given the data
Mm.
because they are not asking about that specific, right? So if we have to choose one, then we cannot because they haven't specified anything, which can
So
help us
cal.
to determine. Not cal, not cal. You will came across. See the next question. I think we have to use a value. See this.
I'm just saying it's cal. I know it's not, but I'm just saying.
It might be cal, but we have to see the
Mm.
units, the energy units.
Yeah.
See the next question. It will help you to like it might clear all your doubts that you might be having right now. Try to read
Okay.
this question.
Oh, that's what. Okay, what is
Difference
different?
between difference
What
between
is the difference between heat of reaction at constant P and constant V for reaction?
this is your chemical reaction. So you have to use which formula? The one with delta energy, Ng,
Oh, yeah.
right? And what they are asking? They
Uh-huh.
are asking the difference between your heat exchange at constant pressure and
Mhm.
constant volume. So what is heat exchange at constant pressure and constant volume? Heat exchange at constant pressure
Okay.
is your delta enthalpy. At constant volume,
Yeah.
it is internal energy. So
Internal.
they are again asking you what?
The
This
same
question.
question.
But they have given you more data. They have given
More.
you this Kelvin, Joule. So for Joule, which value do we use? See, for Joule, we have to use the
I
8.31.
can just,
This one, right?
yeah, for
So now
Joule, we have to use
8.314,
8.314.
right?
But
The- uh,
but they give kj.
calorie, sorry, Kelvin, Joule. So we have a Kelvin as well.
Yeah.
See,
So, oh, okay, okay. It applies to everything. Okay, okay, okay.
uh,
Yeah, yeah, I understand.
okay. So now let's see where we are. So what we have to find? First of all, we will calculate the delta Ng. So for delta Ng, we have to consider only the gas molecules, right? So here we have one liquid and 12 moles of CO2. So in the product side, what I will write?
Yeah.
12,
So 12 minus 15
15, which is minus 3.
minus 3.
So we will use minus 3 in this
R
case of,
is given 8.3.
hmm, you can
So
either
it's
use
not
8.314. It is
8.314.
8.314, but to simplify things, you can consider 8.3.
And they want cut mark.
No, because
Okay.
the answer that you
That
are going
makes
to
it
get,
easier.
uh, it is not going to be, vary that much from your actual answer.
Okay, then minus 3 into 8.3 into temperature. Yeah, they didn't give temperature.
Temperature should be in Kelvin. It is given in Celsius. You have to convert it into what? Kelvin,
Kelvin.
right? How you convert
Okay.
it in Kelvin? What was the formula?
Um,
273 plus.
273 plus Celsius.
So it is going to be how much? 398, I
Um,
guess, or more.
wait.
No.
Is that
300,
373, right?
373 plus 25. How much is it? 298, I guess.
298, yeah.
Sure.
Yeah.
Okay, so it is going to be 298. And
Did they
what
round
will,
it off to 300?
yes, I would suggest
Okay.
you to not do this in your exam. Try to take your answer as accurate as possible. But if you are on
Mhm.
like short on time, you can do this conversion like round off. Okay.
Okay.
After solving this, you will get your answer in kilojoule. This
Mm.
is your kilo, right? Is it
Okay.
making sense?
Yeah, it makes sense. I have a doubt.
Yeah, go ahead, please ask.
Not according to this, like not about the topic. I want
Mm,
to say like in a maths. Well,
mm,
sometimes they include zero in decimals in the last decimal.
mm.
But sometimes they ignore that. Why is that?
Um, Let me write what you are trying to say first. You are saying something like this. 3.0100. Sometimes they write it like this, and sometimes they just write
Yeah,
it like this.
yeah.
Huh. See, both of them have same meanings, right? If you are calculating, if you are solving with the help of this, if you are calculating with the help of this, you are going to get the same answer, right? But
Yeah.
but uh, I don't know. I might not be able to answer it correctly, but let me try. What could be the reason about it? Mm-hmm. See, if we are ending with zero now, we can just cut it short till here. But I don't know why. I don't know why they do this. But if I write like 8 here, then it changes the entire thing. So if you have a 0 at the end, it, if for significant figures, it has a like number, like they have different significant figures. Here we have 5, 1, 2, 3, 4, 5. Here we have 3. The significant
Yeah.
figure thing, we have to like be concerned about the zeros that we are putting after the decimal. But apart from this, if you are doing the normal mathematical calculation, I don't think it matters, because you can do the calculator stuff, you will get the same answer whether you are putting those two extra zeros or not.
Okay.
And I would suggest, like, if you are solving the questions and it is not about significant figures, then you should avoid adding these extra zeros, because they don't have any significance in
Okay,
your actual
fine.
answer, right?
Yeah.
So what else we have? Now you were asking me now how, like, if I am supposed to calculate only delta H or delta E, delta U, so how the question is going to look like. So this question will help you to understand that as well. So I would request you to please read the question and tell me what is given and what they are asking.
Okay.
Meantime, let me take some water from you. Right. Just read the question. After
Please
this,
send the PDF of this.
see in your previous PDF, I will send the PDF, the modified one. I will send it.
Yeah, because there is your homeworks, no?
I will send it. No worry. For now, just read this question, right? I'll go. Let me turn off my mic.
Can you give me 5 minutes?
Sure, sure, sure.
Okay.
Please let me know when you're back. Okay.
Okay.
So can you tell me what is given and what they are asking in the question?
For combustion of 1 mole of C6H6, um, at 27 degrees Celsius, the heat of reaction at constant
Pressure,
P
pressure.
pressure. Yeah, that's what constant P is.
Okay.
Um, 780.9 calories.
Okay.
Then find heat of reaction at constant volume.
Okay, so they have given you the heat exchange at constant pressure, which is basically what?
Minus is 780.9.
What we
So
call this?
we need to
What we
use delta H is equal to delta U
good.
plus um plus wait
Before
reaction,
that,
right?
reaction.
So if it's reaction, it's RT delta NG.
Good. Before that, you missed one thing. If we are talking about heat change at constant pressure, right? What we call this?
Mm-hmm. Enthalpy.
Enthalpy. So delta H is given.
Yeah,
What we have to find?
and
Delta U.
we need to find delta U. So
So
we'll
what we
just switch it.
we will just put the values. We will calculate. We can easily calculate the delta Ng, right?
Yeah,
And what else? What else? What else? If it is given in calories, where is it? It is given in calories, then the R value that we are going to use is going to be 2.
three,
2, 2.
three,
R is
two.
going to be 2. Yes. Okay, let us go back.
Oh, it is two. It is two. It is two. Yes, it
Oh, yeah.
is two. You
Good,
don't
good,
have
good.
to go back.
Right. So basically what we will do, we will just simply put the values, right?
Yeah, but I want to check the equation though,
See,
like the sign convention.
see. For combustion, see, go ahead.
Okay. It's kind of fuzzy in this what you have written. Can you tell me how you can switch between
See,
delta H and delta U?
see, this is your simple formula, right? Delta
Yeah,
U
delta U plus
plus RT
no no
and
RT delta NG.
we have given this thing. We have to find the other one.
Yeah.
So we will do what?
Mhm.
We will take delta H, delta U here, and we will transfer the NG part on the left hand side.
So won't it be minus delta U? Oh, you
Uh,
took that to the other side. Okay, 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 okay,
uh,
okay.
so the answer delta U that you are going to guess is minus 780000 Kelvin. Or you can write it like minus 780 kilocalorie.
Yeah.
How, see, are you able to calculate delta Ng? How we did this? We have
Um. Uh.
six on the product side, 6 moles on the product side,
Yeah.
and on the reactant side, we have 15 by 2 because we will only consider the gas molecules. After solving this, we will get minus 3 by 2, and we used minus 3 by 2 here. What else?
Go back, go back, go back, go back. It's just same thing. It's just same thing.
It is very
It's
simple, but
just
very simple.
it's the same thing. Like how you do with the constant n and delta n is the same thing. Like
Yes.
in the delta n, a product number of moles in the product minus the number of moles in the reactant only for the gases. And in constant is the same thing. The number of moles in the product minus number of moles in the reactant only for gas. It's the same thing, right?
Uh, for constancy, I didn't get your question. What, like, what are you trying to say? What is the same thing here?
Wait. I think I'm confusing myself. Wait. Okay, yeah, understood, understood. But I want to do when they do not ask reaction, when the n is a constant
For
and
that, na,
temperature.
they will say compression or expansion. You will see a change in volume basically.
Okay, do you have that question? I wanted to.
I don't have that question here, but I will do one thing. I will find and I will assign a homework for that, right? And
Yeah,
I
because
think these
I only know how to deal with delta n, but I don't know how to deal with delta
in
t.
those questions,
What
na, in those questions, what you will observe generally, you will observe a change in volume, or they will say you are applying
change
some
in
external pressure.
temperature?
No, not change in temperature, change in volume or change in pressure. Suppose you are applying some external pressure that will lead to what? Some compression. So you
Yeah.
will clearly see. I will assign those questions as well. Don't worry about it.
Okay.
And do one thing after
You
this class,
said
na.
volume? Wait. Isn't the compression and expansion formula delta H is equal to delta U plus or
Hmm.
minus NR delta T?
Delta T. Yes, delta T.
Then where did V come from? Volume.
See, see. If you are, if see, how does that formula starts? It starts from here, na.
Yeah.
So you can modify it. You can use PV is equal to nRT depending on the questions. If they are specifying
Oh,
about like they will give you in the question and you will decide on the basis of a question which formula you are going to use.
okay.
So uh, this I will remove and I will write the now the zeroth law of thermodynamics. Then we will have our heat capacity. It is a very short topic. This one is going to be very important. Then I have to trim this as well so that you might not find it too hard. And then we have some laws and the thermodynamics will be completed and we'll have then thermochemistry. So let us
Thermodynamics is will be completed.
thermodynamics only. Then we have a small portion which is basically thermodynamics, but I will teach you separately, which is thermochemistry.
Is it in the same lesson?
In your NCRT, they have given you in the same lesson, and they like in your NCRT, it is a separate portion or separate, you can say like uh,
Lesson.
content lesson, but it is covered in your thermodynamics itself.
Okay, okay. It's like a sector. Okay.
Uh, zeroth law of thermodynamics. Let us talk about it. It is very simple. If two systems are in thermal equilibrium with a third system, then the two systems are in also thermal equilibrium. Suppose if here A and B are in thermal equilibrium after suppose initially the temperature of A was 80 degrees Celsius, but after some time both of them are in thermal equilibrium. After some time both of them has the same temperature, right? Because what we observe, temperature always moves from high to low. If you are
Yeah.
if you are putting your cup of tea, it might have a very high temperature initially, but after some time it will be equal, like it will be the same as your surrounding, right? So what we will say, your
Yeah.
system has reached a thermal equilibrium with your surrounding. And what zeroth law of thermodynamics states? It states if two systems are in thermodynamic equilibrium and you have attached a third system, then all the systems are going to be in thermal equilibrium with each other. That's it.
What?
Suppose you have two cup of teas, right?
Okay.
After some time, they will reach a thermal equilibrium, and you have
Okay.
inserted another cup of tea, and you will wait for some time, and
Okay.
that third cup of tea will also have a thermal equilibrium with the rest two.
But that doesn't make sense, does it? Because
It is a normal thing. Go ahead.
the first two cup of coffee will be in another temperature, like lesser temperature, so they won't reach the equilibrium.
After some time, if you have left them for some period of time, suppose you put both of
Mm-hmm.
your cups on the table and you went for like you went somewhere and you came after hour, right? So what we will
Yeah.
see, both of the cup will have same temperature because that heat is lost to the surrounding and the entire thing
Okay,
is
okay,
now.
okay, okay.
And if you are attaching a third cup, then it will have the same consequence. And just try to
That's
read the statement.
that's what it is saying.
It is common sense, right? But it is a law.
Yeah.
Just try to read the law for once.
If two systems are in thermal equilibrium with
Mhm.
third system,
Hmm.
then the two system are also what is that?
Are also in thermal,
Also also in thermal equilibrium.
right?
Okay. So it's just saying that if two systems are equal, then the equal to the third one, then the first two are equal.
That's it.
That's it.
Yes. One note, temperature is an
Mhm.
abstract property and it is not measured directly. We can measure temperature with respect of something else. Suppose in thermometer, how you calculate temperature with the help of change in volume. The mercury which is
Yeah.
present in thermometer that like changes, and on the respect of that we calculate the temperature. So what we can say, what is actually happening? The temperature is abstract. We are just relating it with some other thing to understand what temperature are we having, right? I hope you know it
Okay.
now.
Why do they use mercury other than other liquids?
Because of its special property. Like mercury is in liquidish form now,
Pick.
uh, because of its special property. It
Okay.
can it may give you a very specific reason about it why we use mercury. Let me ask Google uncle. Its unique physical property, including a wide liquid temperature range, high thermal conductivity, and consistent expansion, making it ideal for accurate temperature measurement. Right? Basically, it's unique physical. For a wide range of temperature, it can exist as liquid and it has high thermal conductivity as well. Right?
So
Go
that
ahead.
heat thermometer is just a creation to prove that scientists like trust in science.
You can say that.
Because the thing is, it could be wrong. Like
It
the
could be, but
measurements could be wrong.
see, it could be, but as far like so far we are always doing experiments, right? And if we are
Yeah.
getting a outcome which is meeting our theoretical stuff, then we will say that our experiment is correct. Why we do experiment?
Okay.
To prove that our theories are correct.
Yeah.
Suppose someday you might become a great scientist, physics, right? And you have
Yeah.
made an like law which has not been proven yet. So you have basically broken all the rules of physics. So then we have to write all the laws again. So it's like we say na, like if you are breaking a law, we will go into the jail. But if you are breaking a law in science, then you might get a Nobel Prize.
Okay.
Try breaking laws here.
Yeah.
Okay, so let us
Because
talk
it's
about
just
now.
like compression and expansion due to temperature.
But we have to measure the temperature now, and we cannot measure
Yeah.
it directly, so we have to take some help, a third party help.
Okay.
Heat capacity. What is heat capacity? Let us try to understand it very simply. It is heat required to raise the temperature of a substance by 1 degree Celsius. That's it. What is heat capacity? If you are increasing the heat of a substance by 1 degree, how much heat it would require? It is called heat capacity, right?
How much heat it is required?
To raise the temperature of a substance by 1 degree Celsius.
Oh, the volume.
Not volume, 1 degree Celsius temperature. How much heat I
Okay.
should supply? to increase the temperature of a substance by 1 degree is your heat capacity. And it is
Okay.
represented by C.
That's Celsius.
No, C. This thing degree, it is Celsius. And if I'm writing like only C, it is heat capacity. This
Heat
degree is
capacity.
signifying Celsius, right?
Okay.
Heat capacity, the formula for this is Q by delta T. And for Q, we have Joule. For temperature, we have Celsius, or we can use Kelvin as well. So basically, heat required, which is Q, to raise the temperature of a substance by 1 degree is your heat capacity. And let us see, heat capacity is an extensive property. So let us try to prove it, how it is an extensive property. Suppose if you have a small amount of water and you are supposed to raise its temperature by 1 degree, and you have a whole swimming pool of water, and you are supposed to increase its temperature by 1 degree. So where you will find it easier to increase the temperature? For a cup of, for a small cup of water, or for an entire swimming pool, if you have to increase the temperature by 1 degree? Just think about it. You suppose you are boiling your cup
Mm-hmm.
of tea, and you are boiling the entire swimming pool. Which one will heat first?
Cup of tea.
Right? So it is an extensive property. If you are supposed to increase the temperature of something, it is an extensive property. It will depend on the
Yeah.
amount of the substance. So we have to say like it is an extensive property, heat capacity, and I already mentioned it in the previous thing. Like while we were discussing the extensive part, na, I mentioned that heat capacities are extensive. So I hope now you know why. Because it is very
Yeah.
obvious. Like if you are increasing the temperature of a small thing, it will take less time. If you are doing the same with a very large thing, then it will take more time. Heat capacity is an
Yeah.
extensive property.
Extensive
So,
property. Okay.
so, okay, what we can do is we will stop here. Then we will do the heat capacities in different categories, like how you are talking about heat capacity. If you are considering in grams, it is a specific heat capacity. But if you are doing the same thing in moles, we will call it molar heat capacity. And both of these things are very important. And usually students get confused between specific heat capacity and molar heat capacity. So I will
Okay.
explain it in the next class so that we have a fresh mind and we can absorb all of this. And after that, we